to have improved connectivity for the embedded world. Okay. Okay. Then you have for vector and matrix processing, you have the GPUs, the graphic processing units. The thing is that in graphics, most operations are vector and matrix based. Okay, so matrix multiplication, vector to matrix multiplication, and so on are the main operations that are used in graphics. GPUs, as you know, have become highly used in a wide range of fields, also starting from mining, okay, so cryptocurrency mining and so on, to artificial intelligence and etc. The thing it's the typical thing about GPUs is that they have very good support for floating point operations. Okay. Also for matrix operations, vector matrix and so on, but also convolutions, etc. You have the other class, which are digital signal processors. Okay. The digital signal processors, the main difference with respect to the GPUs is that they are very strong in terms of integer or fixed point operations. GPUs are more around the floating point operations. Okay. Although I don't know why in graphics they used floating point. It's quite a mystery, because in the end you have an fixed point output, okay, a pixel, and you actually don't care if the pixel is moved 2 pixels to the right or 3 pixels to the left. Actually, in the end, you have a fixed point image with fixed point coordinates, okay, and so on. Okay. Okay. And this is GPUs and DSPs. Also, DSPs have, as microcontrollers, quite a lot of interfaces to connect to this, let's say, real world. Especially, they have built-in analog and mixed signal components, like analog and digital converters and digital to analog converters, which okay, things that you need to connect to the real world. Okay. Also, a class of processing cores, which is highly specialized. I put here the hardware implementation of the Java virtual machine, which leads actually to reasonable performance, although not quite as C++ based, but a decent performance for Java programs. Okay, as you know, with respect to C++, in a non-hardware accelerated version of the Java virtual machine, a Java program is a snail with respect to a C++ version. Okay. So these are some examples for processing cores. There, as I told you, their main specification for the processing cores is represented by instruction set architectures. Okay, and which represent the set of instruction for that to be executed by that processing core. So actually, nowadays you have let's say, depending on the instructions, you also have dedicated instructions for specific operations. And for example, in modern CPUs, you have some instruction dedicated for operating system. Okay. In Java processor, of course, you have the Java bytecode as the instruction. Okay. And the things can go. Okay. Of course, you may have different architecture optimizations. For example, you may have optimization regarding the register file. You may have quite a lot of optimization regarding the instruction fetch. And you have this especially with dynamic scheduling or hardware schedulers. When you have pipeline architectures, you know probably that in a pipeline you may have some hazards. You, in the sense that successive instructions may have data dependencies, and actually you have coherency problems. For example, in CPUs, you may have memory interfaces specific, especially the ones for cache memory. Okay, by the way, do you know why it's called the cache memory? Do you know what is the cache memory?
It's a very fast memory which is located on the CPU.
Okay, so it's nowadays it's fast. Actually, the thing with cache memory is that it's always available. Okay. Okay, let's say it's located near the CPU. That's another thing. Do you know why it's called cache?
Because it's not permanent.
No, it's permanent. Okay, because from a programming point of view, okay, so as a programmer, that memory does not exist. Okay, it's hidden. Actually, what it means that you cannot allocate memory, so you cannot put pointers and stuff like this in that part of the memory. Okay, so basically that's from a programmer, it's not in the memory address space. Okay, so it's not there, and therefore you cannot allocate memory as a programmer in cache. Okay, from software. Okay, if you make an malloc, you cannot go with an malloc to the cache zone. Okay, so that's why it's. I will tell you when we're going to make to present when I'm going to present memories. What is the thing with this cache? Okay, it's more related to availability than to speed. Nowadays, it's actually more related to the speed. Okay. By the way, do you like mallocs? You know the
C function.
exactly.
Well, in my case, I like it.
Okay, me too. Okay, because usually I prefer more C++. Okay, because I like a little bit of reusability of the code and a little bit of structure. Okay, so not basic C. Okay, so I like more C++ than other high-level languages like Java, mainly because it's really faster. Okay. And when I'm programming, okay, and I'm not doing HDLs, I really like this thing to have intensive, computational intensive things. And of course, the choice is C++. Okay. Good. So, and also I like to have this full control of the program. In Java, for example, I don't have so much full control because I really like to delete and to deallocate the memory by myself. Okay. You know that the allocation that will give you most of the time segmentation fault. Okay. So as I told you, the specification starts from the instruction set architecture, which has two roles. Okay. First of all, you are doing the hardware based on the instruction set architecture. Okay. However, its most important role it's how you develop the toolchain. Okay, this course, okay, I will present how to design based on instruction set architecture and how to code processing core, which in my opinion it's the most simple task. Okay. However, a processing core, you have to use it. And in order to use it, you need the so-called toolchain. Okay. Do you know which are the basic for programs, let's say, which or four components which make up a toolchain? Or the basic toolchain?
The compiler, the assembler, the linker, and I think one more I do not know.
The debugger.
Oh.
Okay. So you have this good debugger, you know, for example, in GCC, you have this good debugger, okay. The debugger which allows you to debug the software. Okay. So yeah, these are the for the assembler, the linker or link editor, the compiler. Okay, you first need to have the assembler. Okay, in order to develop the compiler. Okay, and of course the debugger. Okay, because debugging it's the most intensive task for a software developer. Okay, so what is quite also in this instruction, because it is linked to this tool chain, this instruction set architecture actually it's very slow in the change. Okay, so from a new generation of processing cores to another to a new generation with respect to an older generation, in its instruction set, changes are minimal and consist only in the addition of one or two instructions. Okay, because any changes in the instruction set may lead to some non-compatibility with the toolchain, and if you have non-compatibility with the toolchain, then you will have non-compatibility with software, existing software. Okay, so basically you need to have this backward compatibility, and that's why removal of all the instruction it's avoided. Okay, it does not happen anytime. Okay, so if you need to remove all the instruction, basically you will have a new generation. Actually, you will redesign the instruction, the processing core from the start. Okay, with the instruction set, with the tool chain, everything. Okay, and new generation processing core may have one or two new instructions, okay, for specific tasks and so on, which will mean that very few adaptation in the tool chain, especially in the compiler. Okay, so also for the example, in the based on the instruction set, you can have a simulator And the thing with the simulator for the processing core is that you can start software development long before the processing core in its physical form will exist. Okay. And I know lots of cases when this happens. Usually when you have the processing core, for example, okay, you want to have it in an ASIC, okay, you have the simulator for it, okay, and you start developing basic software, so on, and then you have the FPGA prototype, and the basic software that ran on the simulator, you put it on the FPGA and you see how it works. You make memory traces and try to figure out some performance issues and so on. And then you start afterwards, you have the physical core. You will just validate and you will extract the new performance estimates for this processing core. Okay. Usually, and this actually allows lots of time to be saved. Okay, so an instruction set architectures actually contains the entire thing that it's related to a processor. So you have the machine level or the byte code for the instruction set. You have the register file, and very important, you have the exception handling. Okay, when you have this exception, and the interrupt handling. Okay. By the way, I have one question. What are interrupts? And do you know how they are behaving? Or how a processor behaves when an interrupt is called?
No, I know it pauses whatever it's doing, looks up some table, and then calls an interrupt handler for that specific interrupt.
Exactly. In principle, that's what it's doing. Actually, in many cases, that call for the interrupt handler, it's not a call. Actually, it goes to a specific address. Okay, for each interrupt or for each type of interrupt, you have a specific address in the memory address space, and in that memory address space, you have this handler, okay, of the interrupt, okay. And another thing, it's most of the cases you save the processing state, meaning that you save all the values of the registers, meaning program counter, meaning a register, data register file, the exception and special condition registers, and so on. Okay, so you save and you go to the address where the interrupt handling routine it's located. Okay, so and that mechanism is highly useful in lots of the cases. For example, in embedded, actually it allows not to permanently interrogate, let's say, some status. Okay, so one event happens. Okay, let's say a counter reaches its maximum value. It will activate a signal which will activate an interrupt, and by default it will go there, okay, to the interrupt handling routine. Okay, and the processor actually via the interrupts can do other stuff while waiting for that interrupt. Okay, you don't have to have, do not need to have instructions in order to permanently interrogate I don't know, some memory locations, some registers, and so on. Okay, so this is with the interrupt. For example, I know that for basic Linux, I have seen the code actually that ran on okay, It was on a processor core on an FPGA. It was a basic version of Unix, okay? And its main, okay, it was int main while one, and this is it. Okay, so the entire processing, the entire operating system was just while one, okay? And actually all the code, the meaningful code, was in the interrupt handling function. So basically the operating system worked just with interrupts, okay? So the main part, okay, was nothing basically. While one, it's actually, okay, you do nothing all the time. Actually, it does because of the interrupts, okay. A second characteristic of the instruction set architecture. So instruction set architecture is specific to a processor. However, the memory map, it's not part of the instruction set architecture. And the memory map is given by the system where the processor is placed, okay? This does not, okay, this does, because it's given by the system, okay, you may have different system configurations, okay, with different memory maps for the same processing core, okay? And this is normal because, for example, in an embedded system, in a different address location, you have, let's say, different types of components. Let's say you have counters, you have GPIOs. The memory starts from another address, okay, and so on. So you have this kind of the memory mapping, which is important from a programming point of view, because in the based on the memory map, you may allocate and you may use the components for the different of the system, okay? The main memory, for example, you use it for the normal variables, okay? This is part of the system description, okay? So it's not, does not come into this instruction set architecture. Okay, so how the processor works? It works quite simple. For example, if you take into account an RISC processor, you read instruction from the memory, you start to read data from the memory, you process data within the processing core, and you write back the data into the memory. Okay, so that's the whole idea. So you need a permanently, you need to permanently read the instructions from the memory, and the part of the memory which holds the instruction is called instruction memory, and the address where you need to read is called the program counter. Okay, so the address of the current instruction, it's the program counter, and you permanently read from the memory at the address given by the program counter, and this is the instruction read. Okay, you have basically two finite state machines. One finite state machine is based on the program counter, okay, and this program counter, it's default, it's increment its value. However, where you may have two other possible ways. First of all, it's add a non-incremental value when you have branches. Okay, so when you have something like if and that branch is taken, actually this means that you'll jump by several, I don't know, addresses before or after the value within the program counter. And when you have interrupts, you will load into the program counter a predefined value. As I said to you, in the case of interrupts, you usually this interrupt handler call or the function call actually means that you load into the program counter the predefined value. Okay, and at that predefined value you have the code associated to the interrupt function. Okay, the second finished state machine, it's based on the instruction register, and this instruction register actually is used in order to to process data. Actually tells you how the instruction tells you how data is processed. Of course, because nowadays all the processing cores have interrupts and exception handling and so on, you may have finished state machines with these things. Okay. So the processing components, you have first of all registers, and as I told you, the first register is the program counter. The second register is the instruction register, where you store the instruction which is read from the memory, and based on it or on its decoding, you'd perform the operation corresponding to these instructions. And the data within the processing core, it's usually it's a register file, and you have different trade-offs. You may have multiple register file, register file, which is actually are the most highly desirable when you need increased parallelism. Okay, but with the multiple ports, this memory actually increases, its cost increases almost exponentially. Okay, by the way, do you know what is a multi-port memory? So let's say what means a two-port memory?
It allows multiple accesses, like two reads at the same time.
Yes, it allows two-port memories. It allows two reads at the same time. Okay. Okay, in a multiple port memory, there is only one. Okay, there is only one constraint, not to perform two writes at the same address. Okay, which is obvious, this type of constraint. Okay, so for parallel computing, multiple port memory are something like a holy grail. Okay, because if you have multi-port memories, actually you can access that memories at the same time. That's important, from different let's say processing cores or stuff like this. Okay, so the thing with multi-port memories and multiple register file, as I written in the slide, is that the cost actually increases exponentially with number of ports. So the highly desirable is to have one read port and one write port. Okay, so you may have perform one read and one write at the same time. Okay, this is not a true dual port. A true dual port meaning that you perform two reads and two writes at the same time. Okay, so this is with the register file. So in this case, it's you have this data register file, the highly desirable from a software and from Parallels point of view, it's to have a multi-port, but with the cost actually exploding. Okay. I know cases when they had multi-ports, something like 8, and it was madness. Okay. Also, number of registers are the status registers. Okay. And if you have pipelining, you have pipeline registers. Okay. Pipeline registers actually are not the register that you need in when designing the software. They are not within the instruction set, okay, because as I told you, the instruction set architecture allow defines also the minimum registers, okay, within, and the pipeline registers are not within the instruction set architecture, okay. So these are the registers. Also, you have memory interfaces because both the instruction and the data memory are not part of the core. Depending on the kinds of memory interfaces and how you deal with the instruction and data memory, you have von Neumann architecture and Harvard architecture, in the sense that in von Neumann you have one memory for instruction and data, and Harvard you have separate memory for instruction and data. Okay. So usually memory in many processing cores may be used by other system components. For example, in multi-core systems, okay, you have the memory which may be used by multiple processing cores, and actually these interfaces are replaced by bus interfaces. And of course, you have the arithmetic logic unit, which perform actually the processing task by arithmetic and logic operations. You have the interrupt handlers, okay, and you may have I/O interfaces. However, because of the programmability, the I/O interfaces are placed in the system memory address space because, okay, they are easier to program, okay, if they are placed in the system memory address space. Okay, you put pointers there, you allocate the data for that specific register, use the volatile. I don't know, have you used volatile variables, volatile pointers actually?
I'm not sure if there were pointers, but I use volatile to stop compiler optimizations on some variables.
Actually, that's the thing with that volatile, of course, it stops some compiler optimization in the sense. Okay, I will explain you a use case here with volatile. Let's say you have an WART interface, okay, a serial WART interface, and you're on the receiving side, okay. Of course, because you are on the receiving side, you won't write. Let's say, okay, you're not in the transmission. As a processor, you won't write the register allocated to the receiving side, okay, because you're on the receiving side, so you are expecting someone from outside, okay, which is connected to the UART interface to write the data into the receive registers of the UART interface. Okay, so basically, in your software, in your program, you want to update the receiving registers. Okay, so the variables allocated to the registers on the receiving side of the UART won't be updated in your program. Okay, because you're on the receiving side. Okay, so because you won't update, okay, if you don't put that volatile, actually the compiler will say, okay, that variable it's not updated. You won't even initialize that variable. Okay, so that variable it's not updated, it's not initialized, so on. Okay, and actually it's not used because it's not updated, and I will and the compiler will remove that variable. Okay, and by placing that volatile, actually you won't allow this compiler optimization, that removal, because you're going to use the variable but you won't update it because it's the variable will be updated by the external event which is the transmitter for that UART interface, which is not the processing core. Okay, so this is the thing with the volatile variables. Okay, and which are highly used for in embedded. Okay, especially when you're not using dedicated APIs. Okay, which actually make that embedded programming looks more like a toy things. Okay, good. So we are going to go to the MIT beta processor. Today I'm going to pass a little bit to the instruction set, and with coding we'll proceed next week. Okay, so the beta processor, it's an educational CPU for, it was developed for MIT student, 32-bit RISC processor. I will exemplify with the Harvard architecture, meaning that I will have two memory interfaces for instruction and for data. Okay, RISC processors are easy to pipeline. Okay, and you have this little endian convention, meaning that byte 0 for a 32-bit word is at lower address. The big endian, it's the opposite. Okay, so byte 0, it's so basically, for example, if you consider the memory to be on a byte level, okay, that's an legacy convention. Then okay, the 32-bit word, okay, requires 4 addresses, and the thing is where you put how you put the data. Okay, and the little endian, it's with the byte 0 at address 0, byte 1 address 1, byte 2 address 2, and byte 3 address 3. Big endian is the opposite. Byte 0, it's address 0. Okay, so okay, the most trivial it's to use the little endian, although the PowerPC from IBM, I think, uses big endian convention. So the registers, they are 32-bit register with some dedicated registers. Register 31, which is an always 0, register 30, which is an exception pointer, register 29 stack pointer for call, 28 the link pointer, and 27 frame base pointer. The program counter has a dedicated bit, which is the most significant bit in order to enter the so-called supervisor mode. And this will be done by setting the bit for the program counter. It can enter into the supervising mode only by only via exceptions. Being a RISC architecture, it's quite a simple instruction set in the sense that it has 3 types of instructions. The instructions with memory operation, which are load store, the ALU instructions, and control instruction, which are branches, both unconditional and both conditional branches. So for 32 register, you have 5 bits for register encoding. For the instruction, for the opcode of the instruction, you have 6 bits. And actually, in the next slide, you will see examples of how instructions are encoded. So, for example, in the ALU instructions, usually in most processors, you have 2 types. One type is operation between the registers, and it will start with an opcode. Then, let's say, destination register, source register 1, source register 2. Okay. Regarding the and also for ALU instruction, you have also operation between a register and a constant, and the constant is given in the instruction. So basically, the last bits of the instruction, the last significant part, it's are dedicated for the constant. Okay, and here you have an example of an opcode for an instruction. And these are the ALU, the opcodes for ALU instruction type 1. Okay. And here are the opcodes for ALU instructions type 2. Okay. So basically, based on the opcodes and on the different registers encoding here, you are performing the operations given by these opcodes. Okay. Branch instructions, you have a 6-bit opcode, a 5-bit destination register, 5-bit source register, and 60 bits constant. And actually, in the end, you will load into the program counter, in the case of unconditional branching, the address of the branch instruction, which is actually the source code, the source register plus the constant. Either for conditional branching, you will have a conditional load into the program counter. And here are the branch instruction and what are the operations for these branch instructions. And last but not least are the load store, and again you have load store and the so-called relative load, with the source and constant registers used to compute the memory address. Okay, the destination register is okay. So for example, in the case of the load, you have you will put in register 3 your load data for this address, in the store, in the memory at this address you will transfer the data found into this register, and the relative load is based on the program counter. Okay, so these are the load store instruction. In this example next week, we will cover on a two-stage pipeline. The first stage, it's actually an instruction fetch and decode. The second stage, it's an execution load and store. Usually there are pipelines with no pipeline, up to 5-stage pipelines. More than 5 usually has the problems of increased frequency for data hazards. Okay, so supervisor instruction that are dedicated, you may have supervisor which are executed only in supervisor mode, and here are exceptions and interrupts, which we won't cover in the next week, in the sense that we won't develop the code for this interrupt and exception handling. Okay, so as I told you, you have when you develop a processor core, you will need the the RTL code for the processing core, which allows the physical implementation, or the FPGA prototype for the processing core. But you also need the part regarding the usability, and this means that you need the tool chain. But with the tool chain, you will have bare metal programming, and also nowadays you need this operating system kernel, which allows actually virtual memory, file system, threading, and so on. Okay, so this is for today. Next week we will have the RTL code for the simplified beta processor. Okay, thank you. If you have questions. If you don't, we'll meet next week, Wednesday at 8:20. Thank you. Goodbye.
Thank you. Have a nice day.
Okay, bye.
Bye bye.